Heat and temperature. These are two terms that people often think means the same thing, but they don't. It's important as physicists that we have these definitions correct. So, what is the difference? Let's look at the two items on screen now. On the left is a cup of coffee, and on the right is a lit match. It should be really obvious to you that the match is much hotter or at a higher temperature than the cup of coffee. But it's not so obvious that the cup of coffee actually contains much more heat. In order for us to see this clearly, let's zoom in and look at the particles inside. In the coffee, there's millions of particles, all moving fairly slowly. But heat's a measure of the total energy in a system. So if we add up all the energy of every particle, we find there's loads of heat energy there. Now, if we look at the match, we see there's only a handful of particles, and although they're zipping around really quickly, because there's so few of them, if we add up the total energy here, we find it's much lower than in the coffee. Temperature, however, is a measure of the average energy in a system. And as we can see in the match, the particles are moving much faster than in the coffee. So the average energy, and hence the temperature, is much higher. To recap, heat is the total energy in a system. And because it's energy, it's measured in the same units as energy, which is joules. Temperature, however, is the average energy in a system. And there's loads of different units for temperature, such as Celsius, Fahrenheit, and Kelvin. It's really important to make sure you remember and understand these basic definitions as we move through the rest of the heat topic.
This is part of one of 11 videos on heat and the kinetic theory of gases. Details are available from the physics website. The purpose of this video is to derive an equation relating the macro properties of a gas to the micro properties. In the first instance, imagine a single molecule rebounding backwards and forwards inside a box. If we freeze this molecule just a few moments before it hits the right-hand face of the box, the momentum of the molecule will be mv, where m is its mass and v its velocity. If it rebounds elastically from the end of the box, then its momentum will be mv, but in the opposite direction. Remembering that momentum is a vector quantity, the change in momentum is then mv minus mv, which is 2mv. Remember that we're making the assumption that the collision is perfectly elastic. The next step is to calculate the force on the shaded green face. To do that, we need to know the dimensions of the box, so we give it length L, width W, and height h. The molecule will rebound from one end of the box, along to the other, rebound there, and then back again. In this time, it covers a distance of 2L. Since it has a velocity v, the time taken, distance divided by speed, is 2L divided by v. Here again we're making an assumption. The distance that the atom or molecule will actually be travelling is slightly less than the full length of the box due to its own size. So we're making the assumption that the diameter or size of the atom or molecule is insignificant. Neither are we making any allowance for the time of the collision. We're assuming that that time is absolutely negligible. It is important for most examination boards that you make a note of these assumptions we're making. When the particle hits the side of the box, there is a force on the face due to the reversal of the momentum of the particle. Derived from Newton's laws, the average force on the face is equal to the rate of change in momentum, that is, the change in momentum divided by the time taken. We've seen that the change in momentum is 2mv. The time taken is that for the molecule or atom to travel up the box and down again. We have already calculated that, and the time is 2L over v, which cancels and resolves to mv squared over L. The average pressure on the face is the force divided by the area. That is the force mv squared over L, all divided by W times h, the area of the face. This gives mv squared divided by LWH, but L times W times H is the volume of the box. So we replace that with capital V for volume. Now, of course, we expect that there are a large number of molecules in the box, all going backwards and forwards. We don't know what that number is, so we'll give it simply the symbol capital N. So the force on one face due to n molecules bouncing backwards and forwards will be n mv squared over v. And of course the molecules won't just be going sideways, they'll be going up and down and backwards and forwards. Because there are three possible directions in which they can travel, the average force, therefore, is divided by 3. In making this general assumption that the molecules have a similar effect in every direction, we are particularly assuming that there are a very large number of molecules and that their motion is entirely random. This proof relies upon the molecules moving at uniform speeds and in straight lines, even when there are large numbers. Consequently, we're assuming that there are no forces between the molecules to disturb that. We have moved on to the point where we have a general expression for the motion of gas in this box. It is that the pressure is equal to the number of particles times the mass of 1 multiplied by the velocity squared divided by 3 times the volume of the box. But of course we must recognize that within this box and a large number of molecules, the collisions between molecules will mean that their speeds are not all the same. We cannot simply use an expression for average velocity because velocity is a vector. And for every molecule moving up, there'll be one moving down. For every one moving sideways, there'll be one moving in the opposite direction, and so on. The average velocity would be 0. It would make absolutely no sense to substitute a value of 0 in this equation, so we turn to the concept of. See the website for details of more videos in this series.
The first law of thermodynamics is generally referred to as the law of conservation of energy, which means that energy can neither be created nor destroyed, but it can change forms. It can also be stated that the total amount of energy in a closed system remains constant. There are several ways in which the first law of thermodynamics can be expressed mathematically. The most general expression of the first law would be that the sum of all changes in energy equals 0. The simplest possible expression of this is that the change in energy form 1 plus the change in energy form 2 equals 0. In dealing with heat and work, the formula is the change in internal energy equals the heat added to the system minus the work done by the system. In a gravitational field, it is the change in potential energy plus the change in kinetic energy equals 0. In this illustration, the red circles represent energy. Note that you can move the energy around all you want, but the total amount remains the same. The same thing goes for actual energy. You can move it around, change its form, but the amount remains the same. The significance of the first law is that the total amount of energy in the universe is constant, so it is impossible to get more energy out of a system than is put into it. Simply put, you can't get energy from nothing. Furthermore, any system that puts out more energy than is put into it from any source is impossible. To be possible, a system must get energy from someplace, even if it is not obvious. This does not mean that you can't get more energy out of a system than you put into it. In classical thermodynamics, free energy is the energy in a system available to do work. However, this is not what this section is about. In this section, free energy refers to a group of devices alleged to put out more energy than the user puts into it. So the question is, does free energy violate the first law of thermodynamics? The answer is no, as long as the free energy device gets energy from someplace. Now, it needs to be noted that there are recognized devices that technically qualify as free energy. These include solar cells that get their energy from sunlight. Now, most alleged free energy devices seek to tap the universe's zero-point energy. While it may be debatable as to whether or not zero-point energy can be tapped, it does not, in principle, violate the first law of thermodynamics. In conclusion, the first law of thermodynamics simply says that the amount of energy in a closed system remains constant, regardless of how it is changed or moved around. To add energy to a system, it needs to come from someplace else.